So here we go. All the well, I shouldn't say that. A lot of the background stuff is out of the way. And so we're ready to start our first bona fide numerical method, transfer matrix method, which is a method I love, by the way, and I use it all the time. As simple as it is, we actually use it in our group a whole lot. So remember the pace of this course that I described last lecture. We're gonna talk you through a numerical method, and then in those week or two that you're working on it, we'll splash in other topics, maybe methods that you're not going to implement, or background for the next numerical method. And then by the time you're done and have that method working, then we go back to the next numerical method. So we're going to sprinkle in more background stuff as we go, but everything in this last lecture you're going to need to know to understand other concepts coming up, like diffraction through gratings and stuff like that. This one's pretty simple, but everything we talked about today, you actually will need to really understand this method, in particular some problems with it and how to fix it. So here we go. We'll just skip by this. So during the first lecture, we discussed the big thing there was preparing Maxwell's equations for solving through a numerical method. And we did several things. We Fourier transformed from the time domain to the frequency domain. The big thing that happened there was the epsilon times E and the mu times H, which were convolutions in the time domain, become just simple multiplications in the frequency domain. So that really simplified. Then we took our constitutive relations and substituted those into Maxwell's equations. And when we did that, we eliminated the D and B fields, so we're left only with E and H. What did we do then? We assumed isotropic materials, I think, and I believe we normalized some parameters, and that was about it. But we ended up with 6 equations. We went to curl equations, the 2 curl equations, we expanded that into 6 coupled partial differential equations, and left it there. We say we pick up on that on all the other numerical methods that we did. So we're going to do that. So the transfer matrix method models a one-dimensional system. So what do I mean by that? Because everything's really 3-dimensional. So imagine we have slabs of material, infinite slabs of infinite extent in x and y directions, which we'll call the transverse directions. But in the longitudinal or z direction, they're finite. They have finite thicknesses. That's what we're modeling here. This is actually a very good approximation for a lot of things, but not everything. If it really is finite size this way, and it's pretty short, you're going to run into troubles with the transfer matrix method. It may still be a good place to start, but then you're going to want to follow it up with a more sophisticated method that we'll learn later. For those of you interested in fiber Bragg gratings, this is your method here. So infinite slabs in this transverse direction, but any thickness you want in this direction. They can be, as you'll discover, they can be miles thick or nanometers thick, and we'll be able to handle it both essentially for free. So that's a picture of what we're modeling. All real devices are 3-dimensional. Any time that we can take a 3D device and reduce it to a 2D, always good practice. And if we can reduce it to 1D, that's always good practice. A lot of times what we'll do, we'll have a slab of material. These colors are horrible, and I keep needing to re-render this. But we have big holes and not a lot of dielectric left here, right? So a good approximation to make is that probably has a lower dielectric constant because it's mostly air. If we make the holes smaller, there's more dielectric here. That probably has a higher dielectric constant. And now we can actually think of this 3D complex thing as a stack of these homogeneous layers, just with alternating dielectric. Great place to start. We may have to follow it up with this once we get our design close and do it real simply. Then this is a much more complex simulation to do. Another place where this is a really good approximation is circuits. So here I'm drawing a microstrip transmission line, and we know by the width of that transmission line we can control the line's impedance, right? So we have some impedance here, some impedance here, some impedance here, and we get reflections at those impedance discontinuities. And so the wave goes in, reflects a little bit from the first interface, but probably mostly transmits. Reflects a little bit from the second interface. That wave comes back, but then also partially transmits. Anyway, you get all this scattering and resonance stuff. Very, very complex, actually, to envision what's happening there. But what we can do is take this and reduce it now to layers of slabs. Instead of having, in this case, some kind of circuit dish impedance, we're going to give it a material impedance. But now these slabs of material is modeling exactly that. So we can model transmission line structures and waveguide structures using the transfer matrix method. Maybe we'll need to follow it up with a more rigorous method because in reality, there may be some spurious radiation a little bit at those discontinuities. And of course, that's not going to account for that. So, but be a great place to start, then maybe follow it up with a more rigorous method. There's a lot of ways that we can reduce 3D to 2D. That was the whole point of that. So for the transformation method, we are modeling slabs of material, infinite slabs of material that have some finite thickness. So here's where we left off with last time when we were preparing Maxwell's equation. So this is where we're going to start. So we went from frequency domain to time domain, substituting the constitutive relations, assumed isotropic, etc. We ended up here. So everybody's good up to here, right? So now the magic starts. So the flow that's going to happen with every numerical method, we're going to have what's called the formulation. And every time we're going to start at Maxwell's equations, and we're going to proceed every painful step until we get to the final equations that we need to enter into MATLAB. So that we'll call the formulation. Then, at that point, we just have equations flying all over the place. We need to tie it together in what we'll call implementation. So you do this equation first, then this equation, summarize it in a block diagram, and then put MATLAB code to it. So there's the formulation and implementation, and you'll kind of see that theme in my slides. We formulate, and then we implement. And so the implementation makes sense of all these equations flying all over the place. Okay, Maxwell's equation. Everybody good? So these layers, when the wave is inside the layer, these layers are homogeneous. We've made that assumption being 1D. We're also going to assume, we're also going to assume a positive sign convention. Right now we're using e to the jk dot r. The reason I did that is I want you to see a formulation with that sign convention. After this method's over, we're actually going to jump to the negative sign convention and do that for the rest of the semester. Because that's the more common thing, but I want you to see both so you can kind of feel that. Anyway, so we have this typical e to the jkr. That's describing the wave in the direction of k, and r is position. Have y'all seen that before for plane waves? So we can take this and expand it out into the 3 different vector components. And we can do the same thing for the H field. Has the same form. Now what we want to do is ask the question, what if we take a derivative in the x direction of this electric field? So we'll substitute in our expression for the electric field, and it turns out only this term is a function of x. Everything else are constants, can come to the outside. And so we just take the derivative of that, so the jkx comes to the outside. So what we're left with is a jkx multiplying the original electric field. So we just write jkx multiplying the original electric field. What this tells us is every time we're trying to take a derivative in x, we just pull out that derivative and put in jkx. And the same thing for the y direction. We just replace it with jky. Now we can't do that for the z direction because it's not homogeneous in the z direction. When you get to the interfaces, the derivative won't be 0. So we can only do that for x and y. Is everybody good with that and comfortable with that? Okay, so we showed in the last slide we can replace a derivative in x, which is jkx, and a derivative in y with the jky. So now we go to Maxwell's equations and do that. And here's the 6 equations that we end up with. So the x and y parameters are now gone. The only independent variable left is z. So that's the only derivative we can take. So in fact, its derivative becomes ordinary. We no longer have partial derivatives. We could still write the partial derivative, but in this case, it's ordinary, because it's the only one left. So is everybody comfortable with this now? The reason we can do this is that it's a one-dimensional simulation. We've assumed it's infinite extent in the x and y direction, so everything's smooth and doesn't really change. So remember our 3 golden rules. We want to normalize, and we think we've normalized too much, we're going to normalize more anyway, kind of thing. So we're doing 2 different normalizations here. One is for the z coordinate. We're going to multiply k0 times z. Remember, k0 is the free space wave number. It's 2 pi over the wavelength. So really what's happening is here is we're taking a dimension, dividing by wavelength, so it comes out unitless. It's just convenient to leave the 2 pi in there. So our normalized z coordinate is k0 times z. And it won't have any units because we had a dimension divided by a dimension, and it's gone. Then our k vectors, which are components of the wave vectors, we are going to divide by this free space wave number. And so we'll have a normalized component of a wave vector. Put the little squiggly over it to denote that normalization. So we're normalizing z by multiplying by k0, and we're normalizing the k's by dividing by k0. And both now become unitless. So if we use these normalized parameters in Maxwell's equations, here's the 6 that we get. And the magical thing that happened there is the k0 has disappeared from those equations. It actually got sucked into our normalized parameters, but it's no longer there. Okay, everybody good? So the next thing we're going to do is, on the left column here, we have our 6 equations that we had on the last slide. We're going to take the 3rd and the 6th equation and solve for the longitudinal component. So we have now equations for EZ and HZ. That's all we did. Take the 3rd and 6th equations, solve for EZ. Everybody good? Now what we're going to do is we're going to eliminate EZ and HZ from our equations. So we're going to take this expression for HZ and plug it into these 2 equations. And now HZ is gone. We're going to take this expression for EZ and substitute it into these 2 equations. And now EZ will be gone. So what we have now are just 4 equations that no longer contain EZ and HZ. They only contain EX, EY, HX, and HY. 4 equations, 4 unknowns. Everybody good? All right. Here we go. Now all I'm going to do is just switch the order and rearrange some terms. What we've done, we brought the derivatives over to the left side of the equation and all the other stuff on the other side. So other than rearranging terms, I haven't done anything here. Just bring the derivatives on the left and everything else on the right. Didn't cancel anything, didn't do anything else. Everybody comfortable with that? Okay, so here's the first magical step, if you will. Here's the 4 equations in the upper left that we had on the previous slide. We have 4 equations, and we can put that into a matrix form. And so here's the matrix form. We have a derivative operating on a column vector containing our 4 unknowns. Here's our 4 unknowns again, and here's the big square matrix that would multiply the set of unknowns to give us all this stuff on the right-hand side of the equations. So stare at that for a second and try to reconcile that matrix, single matrix equation adequately represents those 4 differential equations, 4 coupled differential equations. We're getting there. We're going to start talking about eigenvalues in a minute. Okay, everybody comfortable with that? Everybody believes me? Not lying? Okay. So this is an aside. We made this approximation of isotropic materials. So if you wanted something that was anisotropic, here's that same matrix equation, a bit uglier. And it's kind of a nightmare to implement because there's a lot of little subscripts that you have to get right. And it's a pain. But it can be done, and there it is. That's the answer. We're not doing that here. But you can do it for a project if you wanted. I'm just hearing sighs and grunts. So nobody's going to do that. You know, a lot of cool stuff happens with anisotropic stuff. We're actually doing a lot of research in that. But I understand. Okay, so we've now cast Maxwell's equations into a matrix form. Now we want to solve that. So I'm going to rewrite that big ugly matrix equation we have in a real compact form. And we'll call this bold psi is this column vector of our unknowns. And these are a function of z. They're changing in the z direction. And this big matrix here, we're just going to call omega. So now I can real compactly write my matrix differential equation this way. Everybody comfortable with that? Probably have never seen that treated before. And we can actually solve that as a matrix differential equation, and that's what we're going to do. Actually, we're going to do that quite a bit throughout this semester. Well, MATLAB will, not us. Okay, so everybody's good, right? So we have a pretty simple first order differential equation, and it's a derivative of our function minus that function times a scalar equals 0. So what minus its derivative, or what's derivative minus itself equals 0? It's an exponential, right? We're talking about complex exponentials because they're the derivatives of themselves. So that's the solution. And we can solve this matrix differential equation and write a matrix solution. This is a bold psi. Remember, that's the column vector. So that's our solution. Our four fields as a function of z is an exponential with that matrix omega up there times our initial values for those four fields. So now the question is, we have an exponential of a matrix. What on earth do we do with that? Well, you have the next slide in front of you, so you probably know. But so we can talk about functions of matrices. If we perform some function on a matrix, there's a real clever way we can figure out how to do that. Because it's not clear. How do you take the square root of a matrix? What does that mean? We're not taking the square root of each individual element. We're doing something else. Likewise, exponential. We're not taking an exponential of each individual element. We're doing something else. Well, what is that, and how do you do it? In fact, I have a whole book on functions of matrices. So I boiled it all down to one slide for you guys. So what we do is we'll take this matrix A and we'll solve it as an eigenvalue problem, and we'll calculate its eigenvectors and eigenvalues. So if you have matrix A, if it's a 10 by 10 matrix, you're going to come out with a 10 by 10 matrix W and a 10 by 10 matrix lambda. W is going to contain what we'll call the eigenvectors, and lambda is going to contain what we call the eigenvalues. And they come in pairs. Every eigenvector has an eigenvalue. And in fact, the first column in W, the first eigenvector, corresponds to the first eigenvalue. So that's how they line up. So they correspond, they always come in pairs. The eigenvalue matrix is what's called a diagonal matrix. It's a diagonal of scalars. And so those are all the eigenvalues running down the diagonal. At this point, we don't know what those mean. They're just eigenvectors and eigenvalues. And later on, I'm going to try to draw some pictures to explain physically what those things mean. But we have this matrix A. We want to perform a function f to it. So we calculate its eigenvectors and eigenvalues. Once we have that, here is how we calculate that function. We perform the function on the matrix lambda, that's very easy because all we got to do is just take the exponential of those individually. We can do that because it's a diagonal matrix. So that's easy to do. And then we just pre-multiply by W and post-divide by W. And if we do that, that is that function operating on A. That's kind of crazy, isn't it? The other thing even crazier is I don't know what that's called in math terms. And even though I looked through that entire book, I can't find this. I see it used, but I can't actually find what that's called. So if anybody is mathematically inclined and want to do some research and figure out what that is.
I used to know.
I don't know. But anyway, I do know it's true and it works because I used it a lot.
I'll have to go through my linear algebra notes because this is all very familiar.
I'm not sure you would have seen that in your basic linear algebra class. I don't know.
Not linear algebra. The course Dr. Sarfati is teaching.
Okay.
With the linear algebra. Solving these things, it's all bringing back interesting memories of that class.
But anyway, we have a fancy way now of performing a function on a matrix. It can be square root, it can be exponential, it can be anything. Here's a pretty cool way of doing it that's very easy. Except we have to calculate the eigenvalues and eigenvectors. But that's one command in MATLAB to do that. Okay. So, here was our differential equation, and here's our general solution, but it had that matrix exponential which we had to deal with. So now we know we're going to calculate the eigenvectors and eigenvalues of that matrix omega, and so now our complex exponential is going to look like this. W times the exponential of the eigenvalue matrix divided by W. And so here's what that exponential, the lambda matrix, would look like. It's just the exponential of all the individual eigenvalues. Everybody good? Okay. So now, instead of having this complex exponential multiplying the initial values, we have W times the exponential divided by W, multiplying the initial values. Now, these aren't known yet. And this is a big square matrix of whatever numbers happen to be in there, the eigenvectors. So if we multiply these two, we're just going to get another column vector back. And so since we don't know the initial values, we might as well just group them together and call that C for arbitrary coefficients. And then that's one less matrix multiplication we have to do. So that's what we're going to do. So in fact now our solution is going to look like this. W times the exponential times some kind of column vector of coefficients. And so then here's how we would relate that back to our initial values, which it turns out we're not going to need. But. Okay, is everybody comfortable with that? So we now have our solution. We solved a matrix differential equation, and there we are. Everybody good? So let's dissect this solution to understand it a little bit better. The leftmost term, the psi, that's the overall solution. Those are the actual fields. And if we know that as a function of z, we could plot the fields and see them. So that's the overall field. The W is the eigenvector matrix. This is describing the eigenmodes of the system. So in other words, what are the fundamental configurations of Ex, Ey, Hx, and Hy that can exist in this slab of material? And I have some pictures coming that'll help put physical meaning to that. But each column represents some combination of those four values, which is a wave, an independent wave that can be traveling through this material. The exponential, that's describing the propagation. So they're probably going to be complex numbers if there's waves, right? Because we got to push it. So lambda is going to have a complex number in it. So it's describing decay if there's loss, growth if there's gain. Probably a complex number in there to describe waves, to push it along. That's where the exponential comes in. And then C are weighting those individual modes. We have all the modes in W that propagate according to what's in that exponential, but we don't know how much energy is in each one of those modes. That's what's described in C. is the amplitudes of each of those modes. And we can selectively put more energy into one or the other. So that's how we interpret our solution. Everybody good with that? Piece of cake? All right.
We'll see when it comes to the implementation, right?
A large piece of cake. All right. So now we're going to try to get a feel for the numbers. So here's an example. If we choose a slab of material with dielectric constant 9, we will ignore the magnetic response. So permeability will be 1. Dielectric constant is 9, which means it has a refractive index of 3. And the wave's at normal incidence. This ends up being the omega matrix. And if you go back to the original equation and you plug in the numbers and stuff, that's what you'd get. Since we have normal incidence, kx and ky are 0. And that's why it reduces down to something simpler like this. If kx and ky were not 0, so we're coming in at an angle, you'd see more numbers and more positions there. But that's what it looks like. So normal incidence, dielectric constant of 9. Then if we calculate the eigenvalues and eigenvectors of that, that's down there, W and lambda, the eigenvector and eigenvalue matrices. We want to try to ascribe some physical meaning to that next. But everybody's comfortable with that? And you could go into MATLAB, you could type in that matrix, and then say Eig omega, and out it's going to come these eigenvectors and eigenvalues. So in W, you take one column, there's 4 numbers. The first number is going to be the amplitude of the EX component of the wave. The second number is going to be the amplitude of the EY component of the wave. The third component is going to be the amplitude of the HX component of the wave. The fourth component is going to be the amplitude of the HY component of the wave. That's how we formulated our eigenvalue problem. And I can't go backwards in here, but I'll refer you back to slide 14 on page 7. And you can see that's how we order them, EX, EY, HX, HY. So those 4 numbers in the column represent the amplitudes of those 4 components. So this makes a little bit of sense. If we have a plane wave, we only have a single X and a single Y. So yeah, an electric field is pointing in one direction, an H field is pointing in another. And so that's what we're seeing. We're seeing one X component and one H component corresponding to plane waves. And there's a picture of that later, but so we'll delay that. But that's what's happening. Those 4 numbers are the amplitudes of those 4 components in the wave. Inside anisotropic materials, that can be crazy. We can have all different numbers in all 4 positions, and the modes look crazy. Now the lambda is describing propagation. And what we end up seeing is J times 3 essentially. 3 is refractive index. We were kind of expecting that. Because that exponential is describing the propagation of the wave. This is where refractive index comes in. There's a J because we ignored loss, so these are purely oscillating. So it's really going to be e to the J 3.0 when we take the exponential of that. There's positive J times 3 and there's negative J times 3. The negatives are talking about backward waves because we have waves potentially going 2 different directions, right? And so there they both are. The positive J to the 3 are talking about forward waves and the negatives are talking about backward waves. So it's all there. So here's, as best as I can come up with a picture of that. We have 4 columns in W, meaning that there's 4 modes. So there's actually only 2 modes, but we have 2 of them going forward and 2 of them going back. And why is there 2 modes? Because there's an X and a Y direction. We can have two polarizations. So 2 modes, but we actually have 4 because there's 2 forward, 2 backward. And so if we were trying to draw these, take this first mode, we have 0.95 amplitude on the HY component. So here I'm drawing the HY component oscillating as it travels in Z, and its amplitude is 0.95. The EX component has a minus J 0.32, so it's a smaller wave, only amplitude of 0.32, and that minus J dictates phase. It's minus 90 degrees out of phase with the H. So that's a traditional picture of a plane wave, and there's a balance between E and H, which is clearly coming from the impedance. Anyway, you can go look at those. The signs in the lambda matrix tell you whether it's forward or backward propagating, and the other ones just tell you the amplitudes of the two things. Everybody good with that? Okay, so now we're going to talk about multi-layer structures when there's more than one layer. What we just did, there's only one layer, and we're inside it, and we solve our differential equation, we know what the modes look like, and we know how they propagate. But now we want to talk about multiple layers and interfaces. So here's how we're going to set up an arbitrary layer inside potentially a bunch of layers. So we'll call it the ith layer. So the ith layer has a thickness of L sub I. So clearly the I minus 1 layer is going to have a thickness of L sub I minus 1. But we're just in here, and all of the modes in here have one coefficient column vector. And this, you have to know it from perspective because we have to selectively excite one mode over the other. So these we don't know yet, and it just depends on how it's sourced, how we designed our layers. But this is telling us how much energy is in the individual modes. W tells us what the modes look like, but we really don't know how much energy is in each one. That comes in C here. So inside the layer, we have the initial values, that's psi at 0. And as they propagate, we can calculate those at any point. They're a function of z. And the z is going to be put in the exponential, and that's what propagates the modes. And at the end, at the very last point, just before it hits the interface, is psi at k0 times L. The reason we have the k0 multiplying L is this is expecting to see a normalized z. So we multiply by k0 to normalize the L. So at the beginning, notation-wise, we have psi at 0. At the end, we have psi at k0 L. Is everybody kind of clear what's happened in that picture? So just by knowing the modes, we're going to know how they propagate through that layer. And if we knew what was in that C matrix, telling us how much energy is in each of the modes, we could actually plot the fields. But we don't know that yet. Okay, so what we just said is this top equation. That's how we describe the field within the layer. And we can put numbers to all this stuff right now except C, because we have to know how it's sourced to know how much energy is going into each mode. But now we're going to look at the boundary conditions. So we're going to look at the fields at these two interfaces. A very cool thing we did was eliminate the longitudinal field components. So we only have field components left that are tangential to those interfaces, parallel to those interfaces. And so boundary conditions requires that they're continuous. That's very easy. It'd be much more difficult if we retain those longitudinal components. It's almost like I knew that ahead of time. That's actually one of the big reasons we did that. And we always try to eliminate variables to get a smaller problem. But we only have tangential components left. Boundary conditions are really easy. So boundary conditions requires that we match the fields on either side of the interface. So let's think about the first interface now. The field immediately on the left side is whatever the psi is in the I minus 1 layer, all the way at the right side of it. So it's going to be k0 times L sub I minus 1. So that's the psi at the very last position inside the layer I minus 1. That has to equal psi sub I at 0, the initial values in that layer. So that is our first boundary condition. Well, if we know we have a k0 L sub I minus 1, we can actually put in, replace that with W sub I minus 1 times the exponential times these coefficients. So we can actually put an expression in for that. And over here, it's the same expression. However, the position is at 0, so the exponential just drops out. And so that's how we say the fields at the very beginning. That's the initial values. That's psi at 0. Does that make sense? Or we're just using the form of our solution. So that is our boundary conditions at the first interface. We do the same thing at the second interface. So on the left side of the second interface, we have psi at k0 times Li. And on this other side, we have psi sub I plus 1 in the I plus 1 layer at 0. Do you want to shut that door? They're excited to get in. They hear what we're talking about, and they're all anxious to get in there. Okay, so we're going to match the fields at either side of the interfaces. Then we're going to put in the form of the solution. And what we see now, we have this exponential, k naught L. And on this side, we don't have the exponential because it's at 0. So there actually kind of is an exponential stuck in here. It's just e to the 0, so it drops out. So those are our boundary conditions at the second interface. That's probably the hardest step in this, is doing those boundary conditions. Does everybody follow that? We do that by matching the fields on either side of the interface, not those mode coefficients. That's maybe an easy thing to confuse. It's not the mode coefficients, C's, that are continuous across the interface. It's the fields. Okay, so now let's define a transfer matrix. It is a matrix that if we multiply by C sub I, if we know numbers for that, if we multiplied by the transfer matrix, we would get the mode coefficients in the next layer. If somehow magically we could calculate that. Well, we have some expressions on the other side that we can do some algebra with, and it turns out we can calculate that. The transfer matrix for the ith layer is simply that, and it's just algebra taking the two equations we derived on the other side, whipping stuff around so that we have one equation then that only contains C sub I and Ci plus 1, and then the thing relating those two is the transfer matrix. And so that's what we get in the end. So that's the transfer matrix for the ith layer. And what that does is it takes the mode coefficients in the ith layer and lets you calculate the mode coefficients in the next layer. So you can already maybe try to envision this process. We're gonna step through layers, calculating the transfer matrix the whole way, right? Okay. So here's really the algorithm. There's our slab again. Each layer is going to have its own transfer matrix, right? So we can set up a for loop in MATLAB. We can go one layer at a time and calculate the transfer matrix and keep multiplying them together. And what we get, we're going to call the global transfer matrix. We're going to get one transfer matrix that's no bigger than any of those individual transfer matrices, but it describes now propagation through the entire stack of layers rigorously. But it's not quite the global transfer matrix yet, because remember, the transfer matrix, take the transfer matrix for layer 1, it relates the mode coefficients here to the mode coefficients on the outside. So when we multiply all these transfer matrices together, we're going to end up relating the mode coefficients here in the first layer to the mode coefficients out here in the transmission region. Really, we want to relate the mode coefficients in the reflection region to the mode coefficients in the transmission region. That's the global transfer matrix. We got one little more step to do. So here's how we do it. We write the boundary conditions at that very first interface and plug those into our equations. And in the end, our global transfer matrix that connects the mode coefficients in the transmission region to the mode coefficients in the reflection region is just this. It's this sort of preliminary global transfer matrix we calculated with these W's. W sub 1, those are the eigenmodes in the first layer, and W sub ref, these are the eigenmodes that exist in the reflection region. So here's our overall global transfer matrix. So we've done it. We have this very complex stack of layers, can be any number, any thickness, and we can rigorously describe propagation through that. So that's kind of exciting, isn't it? Now, there's one big problem with this. It doesn't work. I've just wasted your time. So that's what we want to talk about next. It is inherently unstable, and in fact, there is no such thing as the transfer matrix method. But when we fix it, for whatever reason, the community still calls it the transfer matrix method, even though the transfer matrix method doesn't work. But let's understand why, because then we'll understand how to fix it. Then we'll fix it, and you'll understand I didn't really waste your time. Well, actually, when I was originally designing this course, what I wanted to do was teach transfer matrix method and give a homework assignment to implement it. And then, of course, everybody would get stuck and it's not working, but I realized I'm probably going to cause these poor students hours and hours of work trying to get this to function, and I know darn well in the end it's not going to work. It's going to explode on them. But anyway, so let's figure out why this is not working. Anybody have a guess? Well, if you read ahead, then that's cheating.
Divided by 0?
Sort of. Okay, so let's look at our layers again. So here we are, we've got this intermediate layer sub I and a layer before and after it, right? Now, within that layer, there's only 3 things an electromagnetic field can ever do. And this actually is a global statement. There's only 3 things it can do. And we already know that from our discussion of a complex K vector. It can oscillate, it can decay, or it can do both. So I would say maybe there's 2.5 things and that's it. So think of how simple electromagnetics is. It can only do one of those 3 things ever in any circumstance. Even our more advanced models in 3D, that's the only 3 things the electromagnetic field can do: oscillate, decay, or both. And so that's pictures of that. Everybody good with that? Okay. Well, we remember our solution contains backward waves. Well, they have the same thing. They can either oscillate, they can either decay, or they can do both. Same thing goes for forward and backwards. Now here's the problem. The transfer matrix method, in terms of the sign convention, treats everything as if it's only propagating forward, right? So if you have a wave that's decaying in the backward direction, but you treat it as going forward, what does it do? It explodes, right? So boom. And so the transfer matrix method is inherently unstable because of that. And in fact, people were stuck on this for quite a while and couldn't really figure out why. Not so much in the transfer matrix, but other methods we'll talk about later, like rigorous coupled wave analysis. And they were doing crazy things to fix it until finally a guy named Jim Maharam actually figured out how to fix that. He came up with the first stable formulation of rigorous coupled wave analysis. And that's a method we'll learn here. It's called the enhanced transmittance matrix method. He's a great guy, by the way. He's actually on my PhD committee. I know him well. A very sharp, down-to-earth, personable dude. Very sharp, too. So he really invented the technique rigorous coupled wave analysis. Okay, so that's the reason. It's treating those backward waves, which can decay, as forward propagating, and they explode. So that's bad. Anyway, here's in words. I just said that it's unstable. So here's the fix. When we calculate our eigenmodes, and when I say eigenmode, there's an eigenvector and eigenvalue pair. We know that 2 of them are forward and 2 of them are backward. And we kind of already have a hint of how to fix this. It's those backward waves that are causing us trouble. So in fact, what we need to do is distinguish between the forward and backward waves and then treat them separately. And that's the fix. So the first thing we need to do is look at our W matrix, and there's 2 ways actually we can figure out whether they're forward or backward. We can look at the eigenvalue matrix, look for positive or negatives, or we can look at the field components in the W matrix and look at the pointing vector, because E cross H is the direction that the power is going to flow. And we can do either, and hopefully they give us the same answer. I don't know if there's any weird circumstances where it wouldn't, but they should give us the same answer, so there's 2 ways. But the point is we identify which of those eigenmodes are forward and which of those eigenmodes are backward. So on the left here, we have our original W and lambda matrix. And don't depend on these occurring in any certain order. This, it just happened to be plus, minus, or forward, backward, forward, backward. It could have been plus, minus, minus, plus. That can happen. So you can't depend on any kind of order. But what we want to do is sort them. So the first two columns are going to be our forward waves. The second two columns are going to be our backward waves. Now remember, eigenvectors, eigenvalues occur in pairs. So if we're swapping columns around, we need to do the same thing to the W matrix that we do to the lambda matrix and vice versa. So we swap them together. They always stay together. Otherwise, we're going to end up propagating one mode with another mode's propagation constant, and that causes craziness. So we're sorting the eigenmodes so that all the forwards are on the left and all the backwards are on the right. Now within the forwards, we don't care about the order. We just want the first half of the columns to be the forwards and the second half to be the backwards. Make sense? And don't worry, you're not actually going to have to do this. In our next lecture, you actually won't have to do this. So here's the new interpretation of these matrices. We have the eigenmodes for the forward, eigenmodes for the backward, and we also have our eigenvalues. We have this sort of a forward exponential here and a backward exponential here after we've sorted it. So we need to figure out which is backward, which is forward, sort them, and that's where we end up and how to interpret it. Very good? Okay, so recall that was our original differential equation. It's a matrix differential equation. The psi is a column vector with 4 elements in it. This omega is a 4x4 matrix, and we had a solution in this form. But this contained at the same time forward and backward waves scrambled in some order. Then we go ahead and we sort it, and this is now the form of our solution. And so, what time is it? Do we have time to start the next lecture? Yeah, we got a little bit of time. So that's where we're going to pick up in the next lecture. Any questions on that?
When you were adjusting the lambda matrix, why was it that the diagonal stayed in there? I didn't completely understand.
Yeah, all right. So if you purely just swapped the column vector, suddenly it wouldn't be diagonal anymore, so you move it to the diagonal position.
So that's all you're doing, you're just taking the value, keeping it.
Actually, I should make a note of that, because that's a good question.
You're just flipping it back. You're not changing vectors, you're just changing values.
Yeah, so I guess you should say it's not pure swapping. In the eigenvalue matrix, you also then have to move it up or down to put it in that diagonal position. Yeah. Okay, is everybody good with that? How does everybody feel? So if it did work, do you kind of feel like maybe you could get started coding that? Okay.
Yes.
All right, so let's
Start.